Okay, we are Team 15. I'm Drew Harris.
I'm Farah Borhan.
And I'm Haziq Rahman.
And this is our final presentation of Design Phase 3. Okay, so just a brief introduction here of what you should expect to see in this Design Phase 3 presentation. Basically, we have an overview of the entire design process. So we picked out a few key things from all three design phases, and that's what you're going to see in this presentation today. So we have mission statement, project management, customer needs, and into product specifications, concept generation to concept selection, failure modes and effects analysis, product architecture, industrial design, a CAD model, and then we're going to finish off with some economic analysis. Okay, so moving forward, we have our mission statement here. You'll see the actual mission statement document at your left there. And on the right, I've just pulled out a few key details. So we have included in the mission statement is a product description, which for the Arduino is that it is a physical learning tool driven by the Arduino and designed to demonstrate addition. Then we also have pointed out our primary market, which is primary education teaching professionals, and our secondary market, which would be parents of primary school age children.
Okay, so next is the project management. As you can see over here, this is a Gantt chart, which is a tool that we use to keep our team on schedule. And so far we've managed to do so. We didn't left behind in any task, except for prototyping. We just wish that we have more time so that we can focus more on the Arduino coding. And to do so, we probably need to shorten the task A, B, C, and D so that we can enlarge in the prototyping task.
Next is the customer needs. We have interviewed different type of customer ranging from educational professionals to parents. Okay, so their statement, we interpreted their statements, and then this is a summary of the customer needs, and then we categorize into the primary and secondary need. As you can see here, for number 5, it's like, I like the overall look of the model as it attracts students to participate. We interpreted it as the model should be aesthetically pleasing, and we categorize it as secondary need because we want to focus on its functionality rather than its aesthetic. Okay, the next one is that the kit must be safe for my children. Okay, the interpreted need is that the kit must include the safety precautions, and it is the primary need because we need our kit to be safe. So, for our final project, we have successfully accommodated all the customer needs. The next part is product specification. We analyze and summarize our customer needs in this table, which is the quality function development table. Okay. As we can see here, this is all the customer needs, and then we rank it according to their importance. We can see the kit needs to be safe, receive the highest importance rank, and it correlates with the number of small parts, storage, and reusable for many years. And the next part is the program must be simple and easy to operate, and it correlates with the number of small parts and the simple program user interface. Further down the quality function development table, we can see there is the technical importance, difficulty, and priority. Number of small parts receive the highest ranking because we want to minimize the number of small parts to make our kit safe to be used. And then the overall price receive the highest ranking, which is 5, because we want to focus on its functionality rather than its price.
Okay, next we move on to the concept generation and selection of our BRG project. Using the 65 methods, we've generated 9 solutions in total, with 3 solutions for each station. And using the 9 solutions, we've generated a combination of solutions, which you can see over here is STR, STC, PBR, PBC, PTR, and PTC. So the 6 solutions, a combination of solutions, have gone through a screening process, which we've eliminated PBR and PBC, and using the using the 4th surviving solution combination, we've used the scoring methods to select which combination of solution is the best for us, and we've decided to choose PTC because it scores the highest in low cost criteria, safety, and durability. So PTC is actually stands for pulley, cylindrical tube, and cone funnel.
Next is the failure mode and effect analysis FMEA. The team have identified the potential failure mode and have summarized in this table. For the first potential failure mode is the pulley. As you can see, the potential effect of failure is like the pulley fails to lift the balls up to the tube. So the potential cause of this failure is like the string that attached the pulley to the motor is detached from its positions. It received the highest ranking of occurrence because, as we can see in our project, the string can be easily slipped from the motor. Okay, so it received the highest RPN. So the team has prioritized to address this issue. So the recommended action is that to tighten the connections of the pulley to the motor. For our final project, we have successfully addressed this potential failure mode.
Alright, so here you'll find our product architecture. This just gives a detailed overview of our product itself and all of its individual components. So we've got 9 chunks here. The chunks are outlined in red, and each chunk represents one physical component of our product. Inside each chunk we have outlined in blue the functional or physical elements of the components. And of course all of these 9 chunks are part of one large chunk, which is the pegboard that the entire product is built upon. So to go through all these chunks here, we have the entrance ramp. The entrance ramp accepts the ball from the entrance and delivers it to the pulley system. The pulley system is directly connected to the tubes and the motor. The motor powers the pulley system, and the motor itself gets power from the battery, and the motor is controlled by the Arduino. The Arduino is controlled by a computer program which accepts user input. So the computer program accepts user input, tells the Arduino dictates to the motor what operation, and the motor gets its power from the battery. The motor then drives the pulley system, which raises the ball to the tubes. The ball is transferred into the tubes, and then one or more balls are transferred from the tubes to the bowl. The bowl then releases one ball to the exit ramp, and that's the end of the process. But just one important thing to point out here is the modularity of our product, and that's highlighted by the chunks that kind of shows the modular nature of our product. And this gives us a great advantage because, moving forward, if we were to want to adapt our product or change it in any way, we can change each individual chunk without having a great impact on the whole design.
Okay, so next we move on to our analysis of ergonomics and aesthetic needs. So as you can see over here, our aesthetic needs are scored lower in performance rating compared to our ergonomics needs. As mentioned before in the product specification section, our team believes that we've prioritized more on function over aesthetic appeal, and this performance rating reflects our stand. However, the ease of maintenance receives a performance rating similar with the aesthetic needs. This is because that we believe the BRG shouldn't need much maintenance, but we don't want it to be disposable. Next, we move on to the assessment of our finished product. As you can see over here, we've done a performance rating on 5 assessment categories. And most of the category receive a high rating except for emotional appeal and product differentiation. This is because, as mentioned before, emotional appeal and product differentiation falls into the aesthetic needs. So that is why they receive a lower performance rating. And when talking about product differentiation, our BRG project is similar with the parts used is similar with the product available on market. But our concept demonstrated is unique on itself. Okay, so next we move on to our 3D CAD model section. And as you can see over here, this figure is the CAD assembly of our BRG project. This figure is basically a visual representation of the flow for our BRG. And the flow for the BRG is mentioned previously in the product architecture section. So next, we've moved on to the CAD model of our main components. There are 3 main components, which are funnel, tube, and the exit ramp. I've chosen these 2 components specifically because there are a few changes that we've done since the concept generation. And for this funnel, initially it's supposed to be a cone shape. I decided to make it like a hexagon. This is because to add the aesthetic appeal. And next is the the square cubes. Initially, we've planned to use a cylindrical cube, but we've decided to substitute it with a square-shaped cube. Both of these products are easy to be stored because we can fold them into half.
Okay, so now on to the economics section. First part of this section here we have is the investment proposal. This is our investment proposal to VTEPs for the Arduino project. So left side here you'll see is the cash flow diagram, and on the right side there I've just picked out a few key points from it and kind of describing how it works in general. So first column we have the VTEP's expected input. This is on a color scale where the darkest reds represent the quarters of heaviest investment and the darkest greens represent the quarters of lightest investment. And the next column is the return column. We have a constant 3750 expected return. That's based on a profit analysis we did in design phase 1. The net column simply represents the return minus the investment. And that's VTEP's net return on their investment. So to go through the expected inputs here, kind of break them down, we have two large initial investments we're expecting for VTEPs, and that's $10,000 for an injection mold that we'd be using to mold the ABS plastic for each of our components. We also have a $10,000 fixed cost. That's something that's set by VTEPs at the beginning of the project. So those are the two big initial investments. In addition to that, we have advertising expense at $1,000 per quarter and decreasing linearly to $500 by the end of the 12th quarter. And then we also have a product development cost at $750 per quarter, and that starts at the end of the first quarter. That money will be used to kind of help us keep up with competition and to adapt to a changing marketplace. So all of this together, all of those inputs, and based on this constant return of 3750, yields an IRR of 3.2%, which translates to an APR of 12.8%. So that's what VTEPs will see should they choose to invest in the Arduino. All right, so second and final part of our economics section here is the cost sheet. It's a very complicated table. I'm not going to go into all the details, but the main takeaway from this cost sheet is the highlighted number you'll see at the right, $34.05 total unit variable cost, and that's calculated based on 3 essential components that make up that total. So we've got purchase materials cost, and that is going to be the cost of acquisition for each of our components, whether they be made from raw materials or purchased outright. We also have a machining cost, and that's based on a hourly cost of $45 to machine each component, and a rate of 250 pieces per hour. Third and final component of the total unit variable cost is the assembly cost. This is essentially a labor cost based on a wage rate of $15 per hour and assembly times that are calculated in our DFA. Okay, so now to conclude, at this point in the presentation we've gone over a design process in great detail. So I'd just like to point out the last few key points of how the Arduino stands to benefit all of its stakeholders. So firstly, the Arduino has the potential to educate a lot of people. And it has the potential to help people understand one of the most basic concepts of mathematics, that is addition. And that's really the reason, that's the impetus for this whole project in the first place. We also have a really wide market. This is something that will benefit VTEPs in the future because we have the potential to reach a lot of customers. We also have a very simple concept. That's something that I think makes our product super easy to market. And we have an easily expandable platform. So if we choose to expand into other directions in the future, the platform we've created for our project makes it very easy for us to do that. Lastly, as I've demonstrated in the economics section previously here, the Arduino is economically viable. It stands to benefit VTEPs not only monetarily, but in terms of their company portfolio as a whole. So I hope we've been able to demonstrate our project clearly here, and hopefully VTEPs chooses to invest.